Go. All right, here we go. Previewing the fundamental theorem of calculus. Look at that title. Fundamental theorem of calculus. You can tell math people are excited. There's almost no theorems that are called fundamental. This is calculus in a nutshell. But I'm going to explain it, hopefully, in just such a way that you really don't need much prior knowledge. So if some of the other stuff is sort of running back and forth through your head and you don't have it all narrowed down yet, I hope I explain it in such a way that you're like, oh, I totally get that. With a huge, huge conclusion coming up to all this. Okay, consider the graph of the continuous functions shown on the left. This is tough to explain what they're trying to say here. Say we've got some function. I give it to you guys as an assignment. I go, here's the curve. And you got the equation of it. And I make the assignment. I say, okay, choose any x greater than that. And I say, okay, first person, you find the area from, choose an x between a and b. And I say, you find the area between here and here. And then I choose a different x value, and I give it the homework to somebody else. You find the area between here and here. So you're all going to get different answers, but it's all based off the same thing. So every one of you gets an x value, and the answer you get back is the area under the curve, which we've been starting to call the integral, the area under the curve. A little more to it than that, but that's the basic idea, area under the curve. So if we shade in the region of, you just picture your x value, and other people will have different x values they shaded in between a and b, the shaded area would represent the area from a, the beginning of this, to x, whatever x value I gave you. You know, you got 7, you got 2.1, you got 8, you got 11. Everybody's got a different one. So that shaded area would be represented by the integral, and what this integral symbol means, to re-explain it, it means find the area between a and x, so this is the lower and the upper of whatever the function is, and we'll just imagine that I'm going to give you the equation. Maybe it's a nice simple linear one, maybe it's something with a little more torque, x squared, whatever. Let's assume we can do these areas. Notice how the integral depends on what x you choose. You'll get a different answer than other people will get based on what x I give you. Therefore, the integral is a function. Call this function f. So, you guys come back the next day. You all have your answers. Let's presume you got them right. And we got to make a table of values of the answers. 1 comma something, 2 comma something, 3 comma something, 4, 5, 6. Each one of you has an x value, and you give me back an answer, which is the area up to your x value. Your answers will depend a little bit on one another, but basically they'll be independent numbers. So, this function we build will be all the different areas you could get based on the x you choose. Don't let this overcomplicate it in your brain too much. We're just saying, if you came back and we made a table of values of all your results, we'd have all these different answers based on the different x values that you got. It carries over from the previous slide. So okay, this is the important part. That's all fine. You get an area for some x value. You don't have to overthink what that means. Then I say, well, what happens if we take your x value and we just add a little bit? And the picture makes it look gigantic because we got to draw something big to see it. But we're just talking about what happens if you add just a little bit. Now, before we get carried away on this, I want to go back to the circle. Remember we talked about the circle and the area of a circle. If you want to make the area a little bit bigger, you're adding on the circumference. And the derivative pops its head out. It's like, yo, I'm in. If you're just going to go a little bit bigger. Same with volume. Go a little bit bigger, the derivative pops up. So we're going a little bit bigger here. Call the width of this new shaded region h, and that h sort of echoes in your brain, like hits a bell in the back of your brain. You're like, you're back with the h's again? And the answer is big time. There's a reason why h is chosen here, is because that h, we're going to head it towards 0 before this is over. That's what we always did with h's. H has popped its head out, and then at the end, limit as h approaches 0. Okay? So we're just talking about how much bigger does this area get each time we add on a little bit. There's the h. Giant in the picture, small when we actually go to do it. The area of this new shaded region is complicated. Take the area of the whole piece all the way up to x plus h and subtract this piece here. Important little move there. And maybe as you're staring at that, this looks a little bit familiar. Yeah? All we're saying is it's the area up to x plus h. Subtract the area up to x. That's what that little area is. Seems like a nothing move, except it's a huge algebraic move because it starts to build something you've seen before. For small values of h, we see the area of the new shaded region is approximately equal to the area of the rectangle with base h and height f at x. That's what we've been doing the whole time here. In fact, if that's all you got out of the last 4 or 5 lessons, you can follow this lesson, no problem, which is this little rectangle is approximately h wide, and its height is approximately whatever the function value is at x. You just plug it in to get the LRAM or the RRAM or the MRAM. We found out in earlier lessons, it actually doesn't matter which one you use. You can use any one in the section there. Little rectangle there, but we know if we keep that rectangle small, it'll look more rectangular. Yeah? That is, this area is this, but it's also h times f at x, which is big news. Incidentally, I have watched the development of this, no lie, 50 times in my life. When I knew I was going to teach it today, I went on Amazon Prime, found somebody who was teaching it, and just watched their lesson of it, and just sat there reveling in everything that happened there. So if the first time through that you go, ooh, I kind of get that. Remember, it's worth it to just sit around and go and watch that video again and see exactly the development that has to happen here. Because this line is beautiful mathematics. It's the kind of trick we do all the time in math. We find an area one way, we find an area another way, and we set them equal to each other, and then we play around with the algebra to see what we can discover. So it says equals approximately. The facts are it's not equals approximately. If that h is small enough, these things are equal. These are both the area of that little rectangle. As h approaches 0, h f at x becomes a better approximation with equality in the limit. Let's not get distracted by that stuff. That's just the limit as h approaches 0 stuff. That is, as the limit as h approaches 0, this area is equal to this area. Let's review again where these areas came from. One way was just to find this area, we take the big area, subtract the small area. The other way, we just multiplied f at x by h, we just found the area of the little rectangle. Okay, here it comes. Look at him shaking, look at him bouncing around up here. Watch what happens right here. We'll just divide both sides by h. You hadn't recognized that. I made you write it out a zillion times in regular calculus, right? If you did all your homework on the test, you had to do this again and again. That's the derivative. The derivative just popped its head in the middle of us doing integral stuff, screaming at us going, hey, I'm involved here. It comes back to how much does area change? The circumference. How much does area change? By however big the function is. You know, just that little strip there. That's all that's going on there. The derivative of the area is just whatever the function value is. How much are you adding onto the area every time? Just whatever the function value is. That's what you're adding on every time. It's the simplest thing in the world, except it's unbelievably powerful. The derivative of the area is the value of the function. Mostly, that's a pretty deep understanding of it, actually. Therefore, if you want to take the derivative of an integral, you get the function back. This is the completion of something that's been building for a while. Here, listen. This sentence, again, if most of this is like, oh, the details are a little too much for my brain at 2 o'clock on a Wednesday after everything I've been through, just listen to this sentence, and it really shows what's happening there. Adding, subtracting, multiplying, dividing. They're inverse of each other. As soon as addition showed up, it was time to learn about subtraction. As soon as multiplication showed up, it was time to learn about division. Keep going. Squared. Square root. Well, plus or minus square root, but okay, square root. Cubed. Cube root. Exponential. Log. It wasn't far behind. You learned an exponential in grade 11, and then in grade 12, we're like, we got to show you logs. Derivative. Integral. They're inverses of each other. They cancel each other out. They're the perfect pair. It's the question that should have been asked from the beginning. Well, what's the opposite of the derivative? Like addition, what's the opposite? Subtraction. Multiplication, what's the opposite? Division. Derivative, what's the opposite? integral. And these diagrams show that. Even if the first time through you're like, I only sort of get the diagrams, but I'm willing to have some faith in this. Taking the derivative of an integral gives you the original function back. The result is called the first part of the fundamental theorem of calculus. Some books call this the second part. It depends on how they develop them. This is generally thought of as the first fundamental theorem of calculus, or the fundamental theorem of calculus part 1 sometimes it's called, but sometimes you see it the other way around. Don't let that freak you out. In fact, the thing I saw on Amazon Prime had it the other way around. No big deal. It's one of the parts of the fundamental theorem of calculus. Why is it so important? It connects differential calculus, derivatives, with integral calculus, areas. And in that simple diagram, how much does the area change? By whatever the function is. That's all that's happening there. A simple little idea. It says the processes of integration and differentiation are inverses of each other. It says every continuous function is the derivative of some other function. If you have a continuous function, it's come from some derivative. And it says that every continuous function has a antiderivative. First time that word has come up. Antiderivative. It means undo the derivative. Go backwards with the derivative. Example. Here's what you need to be able to accomplish in some homework. Okay? And I want to really over-explain this thing. This is an integral from 5 to x, just like I might have shown on the previous example. Some integral from 5 to x, 2t cos t, and I might give this to you in homework, and first person gets 5 to 10, then you get 5 to 11, you get 5 to 12, 5 to 13, and you go home and do this integral. Maybe you just punch it in your calculator to get the answers. How much does that derivative change as we go down? Whatever the value of the function is at that value. Look how simple it is. How much is it changing? It's changing by whatever the function value is. 2x cos x. You're like, that simple? Mostly. Yeah? Like always, we're going to throw some extra complications in it. Reminds me of this. X squared equals 20. How do we get the square root? Or how do we get the answer? We go x equals square root 20. And when people first see it, they go, so you just put a little check mark deal over the 20, and that gets you the answer for x squared? And those of us who know what's going on go, yeah, that's exactly what it does. Square root undoes squared. And that all seems fine until logs come along. You're like, how do I get rid of exponential? It becomes a log. You're like, so I just write log on the other side and that undoes it? Well, yeah, that's exactly what that does. The derivative of an integral is the function back. There's some details there. There is some details there. The details are you have to be starting at some faraway value over here, 5, up to some x value. And then the derivative and the integral just completely cancel out, and you just end up with the value of the function. But it's right there in the picture. It's really hard, except it's really easy. Right there. How much does the area change by? Whatever the function is. The derivative of the area is the function value. A formal proof of this fundamental theorem of calculus will be studied later. This actually isn't a proof. It's just sort of like, Jesus, sure seems like it's right, but it hasn't been exactly proven yet. It means the integral is the antiderivative of f. So f at x is any derivative of x we get. What's going on there? Lots. It's so simple and so complicated all at once. This d by dx, the derivative, I've brought to the other side. And it becomes its inverse. Add, subtract, multiply, divide, square root, e to the x ln. Here, d by dx becomes antiderivative. Do the opposite of doing the derivative. So this capital F we're going to use, a little confusing when you first see it, to mean the antiderivative of f. How do we do antiderivatives? Oh, we got to talk about that. Let's just presume we can do it. Let's just presume that we can do the antiderivative of that. X squared, 2x squared plus 5x minus 8, for example. Actually, not that hard to do. Yeah? A little harder than the derivative, but not that hard to do to undo this process, to take the antiderivative of it, to find out what the function was that when you take the derivative, you end up with this. All right, so antiderivatives. Put that on the shelf for a second. Like, we got to do some work on how to do antiderivatives. But assuming we can get an antiderivative, the integral is equal to the antiderivative. That easy. Finding the area will be as simple as finding the antiderivative. Let me say that again. Finding the integral will be as simple as just finding the antiderivative. Details. Yes, there's details coming. There's some details coming. Because there's this constant out here. Let's just talk about finding a simple antiderivative, shall we? We'll do the simplest one I can think of. Okay? We'll do antiderivative of 2x. I've really tried to choose something simple. What's the antiderivative of 2x? That is, what do you take the derivative of and end up with answer 2x? Well, x squared. That's simple. That's what antiderivatives are going to be about, is going, okay, what did I take the derivative of to end up here? But there's a lot of functions, actually, that have the antiderivative of 2x. He said x squared. That's the simplest one. But check out if I do x squared plus 5. The derivative of x squared plus 5 is still 2x. The derivative of x squared plus 9 is still 2x. You know, there's some ambiguity here in the antiderivative. We don't know if there was a constant out there. You're like, oh, this is why all that A, B, C, D stuff and everything, finding constants all the time, subbing back in, it's going to come back to roost here, is we're going to have to try and solve for that constant. Because if we want to find the integral, we've got to find an antiderivative, but there's going to be this constant that pumps out every time. The good news is we can find the constant easily. If we set x equal to a, and this is the only thing you really need from the lesson that I skipped over to get to this video, is that the integral from a to a is 0. Anytime you go a to a, say, find the area under a curve from 5 to 5. You're like, there's no area under that curve. Okay, how about from 10 to 10? Yeah, there's no area under that curve. And I get a 0 there. And I can solve for the constant. It's f at a. Here's the result. And it gets, Will, give me the chess stuff here. After you make a really good move in chess, you put an exclamation mark in your little book, right? And how many's the most exclamation marks you're allowed? He says in chess, the really best move in the world that's ever been done, they do 2 exclamation marks. So a Bobby Fischer type move, you get 2 exclamation marks. Like, even the chess master's like, whoa, how did you do that? Yeah. That's the best I can do on a Wednesday to let you know how big a result that is. Now, is it super easy to follow that all the way through? No. Again, we talk about 1 to 10 concepts. There's some things I explain that on a scale of 1 to 10, and by the time I finished explaining, you're supposed to be a 10. You're like, I totally get that. Not this one. This one on 1 to 10, you're supposed to be like, parts of that I was like an 8, parts of that I was like a 2. That's going to take a little while to really get it. But here's the big news in all of it. To find an integral, to find an area under a curve, Josh, Sal, to find areas under curves, find an antiderivative, evaluate it at one endpoint, evaluate it at the other endpoint, and subtract. You're like, you're lying. Just like that, that easy. All those rectangles. Boom, done. Answer, yeah. Same feeling you had was like, wait a minute, derivative of 3x cubed is 9x squared? That easy. No h's, no nothing. Yeah. That's why they were so excited when they were developing this. Leibniz and Newton and those guys. Like, we can do unbelievably hard calculations in a couple of steps. This result is called the second part of the fundamental theory of calculus. Some books call it the first part. It just depends on how it's explained. You can explain one way, and you can explain it in one order or one in the other order. Why is it important? It says that integrals can be calculated without calculating limits and Riemann sums. Without over-explaining it, we're going to do Emmett's integral from earlier now. And actually, This is jumping ahead a whole nother lesson. So the lessons we'll do Friday is basically me doing this. The integral we wanted to do was -3 to 4 of 2x squared plus 5x minus 8. And there's a lot of details there that are going to take a few times watching that to get all the details down. The important result is, if you want to know the value of this integral, the area under this curve from -3 to 4, without doing all the Riemann sums and all that kind of stuff, all the rectangles, first you find the antiderivative. And we almost universally put antiderivatives in square brackets. It's not necessary, but we all do it. We all go, okay, antiderivative. Let's work backwards, shall we? The antiderivative. Antiderivative of -8. What do you find the derivative of to end up with -8? -8x would be the antiderivative. 5x, a little bit more tough, you know, you gotta think a little bit. What do you take the derivative of to end up with 5x? Let's talk about the x for now. Forget the 5's trouble. The 5's out there going, you thought this was going to be easy. It's not going to be easy. What's the antiderivative of x? X squared. And when x squared, you take the derivative of x squared, you get a 2 popping out, and you got to end up with a 5. Well, here's the trick. Oh, Brad. 5 over 2, yeah. So figure out the x first, and whatever you end up as the exponent, just make it a denominator. Actually, that easy. You know, so if you're like, wait, I'm not following, I don't get it. Just knowing that there's a simple little procedure is enough to calm your nerves down and go, okay, I got this. X squared. It must have come from x cubed, giving me a 3 up as the exponent. I need then 2 over 3 there. Antiderivative. Now, this needs to be evaluated, and we're going to go back to see why in a second. It needs to be evaluated at 2 different values. It needs to be evaluated at 4 and at -3. This is where we put it, a new notation here. We want a handy place to put the 4 and -3 after we've done antiderivative. We just write it top and bottom on the square brackets here. Handy place to put it. So the answer here, and I'm not going to evaluate the whole thing. I just wanted to make sure I got to this thing today and said, yeah, we got this. We've got a way to handle it with the fundamental theorem of calculus. Part 2 in my lessons, part 1 and something. So what you do is you go, okay, first bracket, 2/3, 4 cubed plus 5 halves times 4 squared minus 8 times 4 minus 2/3 times -3 cubed plus 5 halves times -3 squared minus 8 times -3 in the second brackets. And that's all we're going to do is evaluate it at 4, evaluate it at -3, and subtract the 2 answers. That's how it says to calculate. Last thing before Maria's question, where's the C? We got to skip out of the C because there'd be a C in this bracket and a C in this bracket. When you go C minus C, they just go. So we get to leave that out in that particular case. Maria. I subbed 4 into this antiderivative. Then I subbed -3 into the antiderivative, and I subtracted. I'm not going to actually figure out the answer here because I'm really getting ahead of myself. I'm actually getting a lesson or two ahead of myself. But I want you to see what this thing does, what the fundamental theorem does. It certainly feels like it, doesn't it? It feels like you're just subtracting 2 areas here. And it's sort of like that, but not exactly. It really comes from back here, this. The thing I put with the triple exclamation mark. If you want to find an integral between 2 values, find its antiderivative at the upper limit and subtract the antiderivative at the lower limit. And I would suspect that you could be as well prepared as possible, all the homework done, everything ready to rock and roll for this lesson. And the first time I explain all that, the most you could probably get out of it would be like, oh, derivatives and integrals are inverses of each other. And to find an integral, I can do antiderivatives. The rest of the explanation is like, while it's happening, I had to get used to that in math university too. Sometimes while a lesson's happening, the best you can do is go along for the ride. Then the next time you watch, you're like, oh, I'm starting to get that. Oh, I'm starting to get that. But the key thing of what we're going to be wanting to be able to do is to do these integrals. Did that help with your question? Yeah. It sort of feels like subtracting two areas, and it sort of is, but there's a little more to it than that. Where was I? It says integrals can be calculated without calculating Riemann sums. That wasn't the most beautiful expression, by the way. A whole bunch of 4s and a whole bunch of -3s and a whole bunch of stuff to sub in. Your calculator can handle all that. No problem, though. But compare that to what we were doing earlier today with the Riemann sums, and hopefully you'll see the power of what I've just done. Especially, here's especially, this way does an infinite number of rectangles. The limit as h approaches 0 was in there. This was always an estimate when we wrote out all the Riemann sums. So this does an infinite number of rectangles in a very low number of steps. Here's another one. I went after yours because I wanted to solve it, but let's try another one and just slow things down a bit. We want to go from -2 to 4 of x squared plus 5. So we need to find its antiderivative. The antiderivative of x squared. Give it a second. Let your brain just process for a second. Antiderivative of x squared. We need something that when I take its derivative, I'll end up back with x squared. Is it right there in front of you? Don't peek. Try and think it through. The trick is to go, well, what am I got to start off with x cubed. And there's going to be a 3 up there as the exponent, so I need that 3 in a denominator to cancel it out. So an antiderivative of x squared plus 5 is x cubed over 5. Antiderivative of 5 is 5x. And so take this antiderivative at 4, then subtract the antiderivative of -2. If a lot of that is blurring by you, that's not what I would try and take out of this lesson if I was you. I'd try and take out of this lesson that you can look at these Riemann sums and go, your days are numbered. Yeah? I got to work a little on finding antiderivatives, which the next lesson on this is just a lot of practice on, let's try this one. What about the antiderivative of this? What about sine? What about cos? What about x to the power 4? You know, like we'll just keep playing around with those. So don't get hung up in that. This lesson is about, simple procedure. Finding the area can be written as an integral, evaluate it by using the antiderivative. And a formal proof will come up later. We'll fit it in at exactly the right time. Oh, also, like inverse trig. Remember we skipped over inverse trig derivatives because I knew I could slot them in at just the right time, and it's coming up. We're going to slot that in. So I'll slot in everything I can with the time we have available. It's too short, Mr. Todd. I need more explanation. I know. The next lesson that I'll teach on Friday will be, well, okay, now that we've seen this, because this is called introduction, it's called preview to the fundamental theorem of calculus. Gives you a feel for what we're going to see. And then practice, practice, practice. I'll do a pile of them on that next lesson. To us, it looks like that's going to be Friday. Okay? But we're going to take a vote on that in just a minute.